I am B. Janardhan Reddy. In this video, I am going to explain specific resistance of materials. Specific resistance is also called as resistivity. In the previous videos, I explained the factors that affect the resistance of a material or conductor. In this video, I will explain specific resistance called as resistivity. What is specific resistance, its units, and resistivity values of some materials will be explained in this video. We have seen in our previous videos that how the resistance of a conductor varies with its length and with its cross-sectional area. See here, shorter wires offer less resistance. That means shorter wires have lesser resistance and longer wires have greater resistance. Simply we can put the shorter the conductor, the smaller is its resistance. The longer the conductor, the more is its resistance. For that reason, here I have shown for small L, R is also small, and for big L, R is also big. Okay, so it can be written as the resistance of a conductor is directly proportional to its length for a constant potential difference. Mathematically, it can be written as R is directly proportional to L. It means that when L increases, R also increases. When L decreases, R also decreases. Let us say this expression as the first expression. Next, let us remind how the resistance of a conductor varies with its cross-sectional area. See here, isn't it? See here. Here, this is a thin wire and this is a thick wire. The thinner the conductor, the higher is its resistance, and the thicker the conductor, the smaller is its resistance. That means a conductor with more cross-sectional area has more area for the charge to flow, so they encounter less opposition. Less opposition means resistance is small. So in this case, the cross-sectional area is small. Hence, it offers more resistance. Whereas in this case, in the second case, the cross-sectional area or the diameter of this resistance, this wire is more. Hence, it offers less resistance. That means when A is small, R is big. When A is big, R is small. Here, R and A are varying inversely. That means the resistance of a conductor is inversely proportional to its cross-sectional area for a constant potential difference. Mathematically, it can be written as R is inversely proportional to A. Okay, so that means when A increases, R decreases. When A decreases, R increases. So let us say this expression as the second expression. Let us combine the above two equations. You see here from the equations 1 and 2 we get. Let us bring back those two equations. Once again you can see here. Just now we have seen R is directly proportional to L and R is inversely proportional to A. Let us combine these two equations and write as R is proportional to L by A. That is, R is directly proportional to L, whereas R is inversely proportional to A. That means when L increases, R also increases. When L decreases, R also decreases. Whereas when A increases, R decreases. When A decreases, R increases. Okay. So let us write this as R is equal to rho L by A. Let us say it as the equation number 3. So in this equation, rho is nothing but it is a proportionality constant called as specific resistance or resistivity of the material. See here, where rho is a proportionality constant and it is called specific resistance or resistivity, and we can rewrite this equation as by making rho as the subject. Let us take cross multiplication and do simple operations. We get here rho is equal to RA by L. So what is rho here? Rho is the specific resistance of a material, isn't it? So rho is equal to RA by L. In this equation, rho is the specific resistance, R is the resistance, A is the cross section area, whereas L is the length of the wire or conductor. So this is the equation to find the specific resistance of a given material. Okay. Now let us define the specific resistance. Definition of specific resistance. You see here, we know that just now we have seen rho equal to RA by L, that is specific resistance equal to resistance into cross section area divided by length. Let L equal to 1 meter and A equal to 1 meter square. Then rho equal to, let us substitute these values in this equation. I am substituting L for 1 and A for 1. We get rho equal to R into 1 by 1 means R only. That is rho equal to R itself. That is the resistance of a conductor itself is equal to its specific resistance when the length and cross sectional area is 1. So we can define the specific resistance as specific resistance is nothing but the resistance only. The resistance offered per unit length and unit cross-sectional area of a material is called its specific resistance. Okay. If we take length of the conductor as 1 meter and the cross-section area 1 meter square, then the resistance offered by that conductor is nothing but its specific resistance. For that reason, here I am defining the specific resistance as the resistance offered per unit length and unit cross-section area of a material is called as its specific resistance. Okay. So here, let us derive SI unit of specific resistance. Here, rho equal to RA by L. We have seen just now. So here, R is the resistance. Resistance is measured in ohms. So rho equal to ohm into area means cross section area means meter square by L is also measured in meters in SI units, and we can write as rho equal to ohm into meter square means meter into meter divided by meter, and here meter gets cancelled here. Finally we get the SI unit of specific resistance is equal to ohm meter, or symbolically we can write it as ohm meter. This is the symbol for ohm. Okay, so the SI unit of specific resistance or resistivity is ohm meter, isn't it? And specific resistance depends on the temperature and nature of the material, whereas the resistance of the conductor depends on nature of material, temperature, and geometrical factors like length and cross section area of the conductor. Okay, here I am showing the specific resistance of some materials. Resistivity or specific resistance of various materials. Here I am showing you in the table. You can see here material, that is the name of the material you can see here, and its rho value, that is rho in ohm meter at 20 degrees Celsius, because the specific resistance varies with temperature, and at 20 degrees Celsius the specific resistance of some materials have been given here. First one is silver. Silver, the specific resistance is 1.59 into 10 to the power of minus 8 ohm meter. Copper, 1.68 into 10 to the power of minus 8 ohm meter. Gold, 2.44 into 10 to the power of minus 8 ohm meter. See here, resistivity values are gradually increasing here, isn't it? Next, aluminium, 2.82 into 10 to the power of minus 8 ohm meter. Calcium, 3.36 into 10 to the power of minus 8 ohm meter. When the resistivity values are less, when the resistivity values are less means they offer less resistance. That means they are the good conductors of electricity. Okay, so we can see that later. And tungsten has the resistivity value 5.60 into 10 to the power of minus 8 ohm meter, and zinc 5.90 into 10 to the power of minus 8, nickel 6.99 into 10 to the power of minus 8, and iron, its resistivity value is 1 into 10 to the power of minus 7 ohm meters. And here you can see the values of resistivity of materials determine their conductivity. Just now I have told you the materials whose resistivity values are less, they offer less resistance. That means they are the good conductors of electricity. So here all these are the metals. Metals with low resistivity behave as good conductors, and metals such as copper are therefore used for making electric wires. You can see here the resistivity of copper is very less. Of course it is somewhat more than silver, but we do not use silver for making electric wires because it is costlier. For that reason we use copper for making electric wires, isn't it? Because it has less resistivity value, that is 1.68 into 10 to the power of minus 8 ohm meter. And the filament of an electric bulb is usually made of tungsten. See here, the resistivity of tungsten is 5.60 into 10 to the power of minus 8 ohm meter because of its higher resistivity values and melting point, that is the melting point of tungsten is 3422 degrees Celsius, isn't it? So the melting point is very high, and the resistivity of tungsten is higher than the resistivity of copper. For that reason, we use tungsten in filaments. Okay? And these are the resistivity values of the different materials here. We can see some more materials and their resistivity in this table also. The resistivity of lead is 2.20 into 10 to the power of minus 7. Nichrome resistivity is 1.10 into 10 to the power of minus 6. Carbon 2.50, that is carbon graphite. Graphite is the allotropy of carbon and its resistivity is 2.50 into 10 to the power of minus 6 ohm meter. Germanium 4.60 10 to the power of minus 1. Drinking water 2.00 into 10 to the power of minus 1. Silicon 6.40 into 10 to the power of 2. Resistivity is gradually increasing. When the resistivity increases, it offers more resistance. Wet wood 1 into 10 to the power of 3, glass 10.0 into 10 to the power of 10, rubber 1.0 into 10 to the power of 13. That is, the resistivity of these materials is very high. Hence, they are the insulators. They do not allow the current to pass through them. Air. The resistivity of air is 1.30 into 10 to the power of 16 ohm meter. Okay, you see here the values of resistivity of insulator. These are the insulators. Glass, rubber, air. Isn't it? These are the insulators. And the values of resistivity of insulator are very high, order of 10 to the power of 14 to 10 to the power of 16 ohm meter. Alloys like nichrome. Nichrome is an alloy. It contains nickel, chromium and iron, and manganese, that is, it is also an alloy. 86% of copper and 12% of manganese and 2% of nickel, and the mixture of these metals is nothing but manganese have 30 to 100 times larger values of resistivity than those of metals. So this makes them suitable for use in the heating elements of electric irons, toasters, etc. Okay, so these alloys also have the advantage that their resistivity or resistance varies very little with temperature and they do not oxidize easily. For that reason, they are used for heating elements like electric irons and toasters, etc. Okay, lead, nichrome, like this. Okay, next, the resistivity of materials such as silicon. For example, you take silicon here, its resistivity value is 6.40 and 10 to the power of 2, and germanium 4.60 and 10 to the power of minus 1. The resistivity of materials such as silicon and germanium are 10 power 5 to 10 power 10 times more than that of metals, but 10 power 15 to 10 power 16 times less than that of insulators. Such materials are called semiconductors. Semiconductors allow the current to flow through them partially. Very small currents are allowed to pass through these materials called semiconductors, germanium and silicon. So semiconductors are used to make diodes, transistors and integrated circuits. Okay, and integrated circuits or ICs are used in all sorts of electronic devices including computer, TV, mobile and phones, etc. Okay, so this is all about the resistivity of different materials. Based on their resistivity, their use is there. Okay, thank you.